There's the sepal width and length, so there's two measures of sepal, there's two other measures of petal, so there's a total of 4 measures. So we can't look at a 4-dimensional picture of what's going on. We can look in 2 dimensions or in 3 dimensions even, but so Fisher, I'm sure, plotted the 2-dimensional things and said, oh, I need something that works in 4 dimensions. You would kind of expect the 2 species to be different from each other. Maybe. So this is the what's called a dendrogram. And this is a stupid one because it's super old. We have better looking ones, and I can show you how. But basically the pictures are going to look something like this. Since you start with all the points, no matter how many you have, they're all in different clusters. The first thing that's going to happen, go back to our picture, is that the 2 closest points are going to be joined together. Well, that distance between those 2 points is what's on this axis over here. I can look at this and go, well, those two points are the closest together. So whatever those 2 points are, they got joined together very first. Then the next step is going to happen, and we're going to join together 2 more points. And I have no idea, can I tell from my picture which they are? Maybe that one? And I can go to the output will tell me if I ask it to exactly which points are joined together at which stage. So do I care if it's, I don't know if this one's higher or those in there, but it's, the next step is those are going to be joined together. And so the dendrogram is a picture that shows you how the points were grouped together. And the software chooses the ordering of the points along here to make the picture look, because otherwise it gets all crossed up and looks not so good. So what's happening here is all the points are being clustered together, and you get down to 2 clusters. This one and that one, and then they don't join together until the distance measure, which down here is at most 0.25, till it quadruples till 1.2 or something like that. So in a 4-dimensional situation, we have 2 clusters going on. But remember, this is 4 dimensions, so we can't see this. But where's the I've never seen this, except in Fisher's iris data. It never is that obvious. And but I bet my tobacco data will cluster very nicely. Even though we're not interested in the grouping the bales of tobacco together, we can do it anyway and see what happens. And I bet it's going to group together the different international ones and the US ones, and it's going to sort of say that we have 3 clusters. And it's going to have a hard time. And so if you were in this situation where we have 2 species, then we might want to see if we group the points together, if the ones within this species group together, the one within the other species group together, and you have a lovely set of evidence without any statistics. Not one statistical thing has happened. We've got the data, and maybe this is why biologists like it. There's no statistics. Don't have to deal with p-values, no confidence intervals, no nothing. Just some math. And out comes a picture that says, wow, those are 2 completely different things going on. And So that's the most famous example. Boring output. Telling your software that you want single linkage. I'll show you how to do this in JMP next week. Your software will ask you what you want to use. And it matters what you tell it. Actually what matters is you want to experiment. And hopefully your answers don't depend too much on the method that you choose. The out tree says you want a dendrogram. And you do, because it helps you interpret what's going on. Those are the variables that are going into the data. And yeah. So again, do you need to know how to write code? No, but you should be able to read code. I can read that and go, oh, I know what's going on. I've never done a cluster analysis in SAS, I don't think. Even the PCB's example. Yeah, let's do this one. So we like our PCBs. They've been supporting the Department of Statistics for many, many years, so hopefully they do never go away. So there'll always be more PCB questions to look at. It turns out PCBs are in two main classes. And boy, I should know what they are. Planar and coplanar. There's two main classes. But evidently, there's 9 Aeroclar classes. I don't know. This is one of Bill's PCB data sets. But since there are 9 classes, then it's certainly possible that they group together based on these classes. So, and we'll talk about doing principal components, because we might want to do principal components. SAS code, we'll skip that because it's boring. SAS output. And the tree happens. The tree doesn't tell you how many clusters there are. But if your tree looks like that, that says that screams 2 clusters. Bill's example doesn't scream in the same way anyway, how many clusters there are. But if you decide how many clusters are there at the red line, 1, which is all these guys down here, 2, 3, 4, 5, 6, 7, 8, 9. The red one. Question?
Are those lines like predetermined?
No. We get to choose.
Okay.
You get to slide the line up and down. It's fun. Now, where should we put the line? Oh, I'll put the line wherever I feel like it, because you get to choose. Presumably, at this, putting the line here, split it up into the 9 classes, which is cool. That means the 9 classes are different from each other. So the points so this is not classification. If we're doing classification into 9 classes, first of all, classification into 9 classes is super hard. It's going to be very challenging. So if I feed this into, I know we'll do our linear discriminant analysis, because that's what we talked about last. But I have 9 groups. And linear discriminant analysis has all this normality stuff going on, blah, 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 blah. Go, no. That's the biologist goes, oh, I'll just do a cluster analysis because I can put it in the software. And if it turns out, again, that this red line gets all the 9 classes grouping together, oh my gosh, you have a perfect picture for your paper. So lots of papers have dendrograms in them. And there's also now there's a 2-dimensional version that the bioinformatics people invented called I forget what it's called. It's a 2-dimensional dendrogram. You cluster you cluster the variables and you cluster the points, and it's a lovely picture sometimes. So that's what we got for pictures. Question?
Yeah, so it looks like there's 93 variables from the code and 54 observations. Does that?
Yeah, that's okay.
It doesn't,
It's just math.
It doesn't matter.
Doesn't matter. It's lovely in the mathematical sense. It doesn't care that there are 93 variables. And a statistical procedure obviously does care. So yeah. So it's a case where Bill was able to use cluster analysis in a really nice way. All right, we'll quit for now. We'll continue next week. Evidence clusters are real. Don't forget to do this. You want some evidence that the clusters are real. We're done. Nope.